What's up, everybody? In this video, we're going to cover USACO's 2017 January contest at the bronze level. Problem number 2, hoof, paper, scissors. You have probably heard of the game rock, paper, scissors. The cows like to play a similar game they call hoof, paper, scissors. The rules of hoof, paper, scissors are simple. 2 cows play against each other. They both count to 3, and then each simultaneously makes a gesture that represents either a hoof, a piece of paper, or a pair of scissors. Hoof beats scissors, since a hoof can smash a pair of scissors. Scissors beats paper, since scissors can cut paper. And paper beats hoof, since the hoof can get a paper cut. For example, if the first cow makes a hoof gesture and the second a paper gesture, then the second cow wins. Of course, it is also possible to tie if both cows make the same gesture. Farmer John watches in fascination as 2 of his cows play a series of N games of hoof, paper, scissors, where N is between 1 and 100. That's quite small. Unfortunately, while he can see that the cows are making 3 distinct types of gestures, he can't tell which one represents hoof, which one represents paper, and which one represents scissors. To Farmer John's untrained eye, they all seem to be variations on hoof. Not knowing the meaning of the 3 gestures, Farmer John assigns them numbers 1, 2, and 3. Perhaps gesture 1 stands for hoof, or maybe it stands for paper. The meaning is not clear to him. Given the gestures made by both cows over all N games, please help Farmer John determine the maximum possible number of games the first cow could have possibly won, given an appropriate mapping between the numbers and their respective gestures. All right. Input format comes from a file called hps.in. You'll have to make a file reader. The first line of the file contains N. That's how many games they played. Each of the remaining N lines contain 2 integers, 1, 2, or 3, describing a game from Farmer John's perspective. So gesture 1 versus gesture 2. So that means the first cow made gesture 1, the second cow made gesture 2. If, for example, 1 was paper and 2 was hoof, then 1 would win, then the first cow would win. If, on the other hand, 1 was hoof and 2 was paper, then the second cow would have win. But either one of those could also have been rock, because we don't know what they are. But anyway, that's the 5 games: gesture 1 versus 2, gesture 2 versus 2, 1 versus 3, 1 versus 1, 3 versus 2. And your output needs to be written to the hps.out file. You have to make a file writer. And then print the maximum number of games the first of the 2 cows could possibly have won. The first of the 2 cows. So that means this cow right here. I don't know that it actually really makes a difference which cow you're checking the maximum of. I'll have to think about that. But basically what it's saying is for this cow right here, what is the maximum number of games they could have won? So the key here is that we don't know what these different values are worth. We've got 1, 2, and 3, and each one could be hoof, paper, or scissors. Hoof, paper, scissors, hoof, paper, scissors. If you haven't already, take a pencil, paper, or take a minute just to think about how rock, paper, scissors work and how you could go about trying to determine. Remember, you don't need to determine what's what. You don't need to determine which number represents hoof and which number represents paper. You only need to figure out who won the most games. So, for example, with 1 and 2, we don't need to specifically know that 1 is hoof and 2 is paper. We could just say, what if 1 beats 2? If 1 beats 2, then either it's paper beats hoof, or scissors beats paper, or hoof beats scissors. But it doesn't matter which one of those it is. It just matters that 1 beats 2. If 1 beats 2, what does that imply about 2 and 3? If 1 is going to win against 2, should 1 also win against 3? Or should 1 lose against 3? What about 2? Should 2 also lose against 3? So it loses against both 1 and 2? Or should 1 and 3, or should 2 win against 3? Think about the implications of that. And if you think about the implications of that, that'll eventually lead you to a path where you realize, again, you don't actually have to know which one is worth what. We just have to decide ahead of time. We've only got 2 possibilities. Either 1's better than 2, and also 2 is better than 3, which would mean then 3 is better than 1, or 1 is worse than 2, which means 2 is worse than 3, which means 3 is worse than 1. It has to be one of these 2 scenarios. Given those 2 scenarios, you can leverage that into a pretty simple solution. So I'm going to pull up on another page here. And we're going to actually, let's look at the original test data. I have 1, 2. Here I've got 1, 2, 2, 2, 1, 3, 1, 1, and then 3, 2. Okay. So in the world where 1 beats 2 and 2 beats 3 and 3 beats 1, versus in the world where 1 loses against 2, 2 loses against 3, and 3 loses against 1. We've got 2 scenarios here. In the first scenario here, we've got 1 versus 2. Well, if 1 beats 2, then that's a win for cow. I'm just calling cow A and cow B. That's a win for cow A because 1's better than 2. Ties can always be ignored. 1 versus 3, that's going to be a win for Cal B, right there, because that would be Cal B winning. Now, on the other hand, in this world over here, so if you look at 1 versus 2 and 1 versus 3, 1 versus 2 in the world where 1 is greater than 2, Cal A is going to be the winner. This is Cal A. I should label this properly. Cal A is the winner on the first one. And then the second one, I'll actually mark the ties just as a placeholder. Second game would have been a tie. Third game would have been Cal B. Okay, but in the world where 1 loses to 2 and 2 loses to 3 and 3 loses to, oops, that should have been a 1. 3 loses to 1. Then in this first game, 1 would have lost to 2, Cal B would have won. Second game would have been a tie anyway. Third game would have been Cal A winning, because 1 is less than 3. Wait, 1 loses to 3. Yeah, because 3 loses to 1. So since 3 loses to 1, then that means that Cal A would have been the winner. So you'll notice these are opposites of each other. Anytime Cal A wins in this variant, Cal B would win in this variant, quite obviously, because if 1 beats 2 in this world and 1 loses to 2 in this world, then obviously if Cal A wins over here, then Cal B must win over here, and vice versa. So when you think about that, as you run through these solutions, which there's only 100 of, you only got 2 possible scenarios that you really have to keep track of. And one of them is the scenario where, again, where they're in increasing order, and one is the scenario when they're in decreasing order. So there's a couple ways to approach this from an algorithm standpoint. One way you might want to do it is to have 2 different variables, one called A win, one called B win. A win, one called B win. And then every time A wins, you would record that as a point. So A win starts at 0, B win starts at 0. And then on this first one, that would be an A win. That's 1 point for A. On this one, that would be a B win. That'd be 1 point for B. If you calculate it down on this side here, then we actually really don't even need this side, because this side is going to be the inverse. Essentially, what you're looking for is what is the most number of games that A could have won. If you were to reverse them, then, for example, if A had won, let's actually go out and calculate all these. But if A wins some number of games and B wins some number of games in this world, then in the other world, it's going to be exactly the opposite. So rather than calculating what happens in the opposite world, we can just know that when we're done at the bottom here, if we were to switch A and B's score with each other, that would be the score that we'd get over on this side. So let's run through this. Let's kind of go through this whole test case, and then we'll think of some other examples to kind of prove that this works. So far, with 1 beats 2, and then 1 loses to 3. So I've got A, tie, and B, and then B, tie, and A. This is a tie score again, tie. Then here's your tiebreaker, 3 and 2. In this case, 2 beats 3, which would mean Cal B would win. In this case, 2 loses to 3, which would mean Cal A would win. So we add this all up. We've got A with 1 game won and B with 2 games won, versus over here, we have B with 1 game won and A with 2 games won. So again, notice that these are opposites, because in this world over here, anytime A wins, that equates to a B win over on the other side. And anytime B wins, that would equate to an A win on this other side. So we don't need to calculate both sides. We really only need to calculate one side. If we run through just one side, I'm going to get rid of this whole thing. If we run through just one side, saying, okay, I'm going to assume that I want 1 to beat 2, 2 to beat 3, and 3 to beat 1. We unfortunately can't do something like if A is greater than B, or if Cal 1 is greater than Cal 2 in this case, because of the 3 beating 1, it's always going to have to loop. So what you can test for as you're running through this is you can look for specific winning situations. If you want to explicitly code it, you can check to see if A is equal to 1 and B is equal to 2, or A is equal to 2 and B is equal to 3, or A is equal to 3 and B is equal to 1. Then you could do A wins plus plus. Obviously, you need to check for equality. That'd probably be the first thing I would check for. If A is equal to B, that's a tie score, and we could ignore it. Do nothing. Else if A is equal to 1 and B is equal to 2, or A is equal to 2, B is equal to 3, or A is equal to 3, B is equal to 1, then that's an A win. Else, you have a B win. Once you're done, you figure A wins and B wins. Take note of the number of A, take note of the number of B, because remember, in the world where 1 beats 2, 2 beats 3, and 3 beats 1, that's what we're calculating. But if we were to inverse A and B, just change the values, then that would be representative of what would happen in a world where 1 loses to 2, 2 loses to 3, and 3 loses to 1. That being the case, then once you're done, all you need to do is between these two numbers, figure out which the largest number is. And whichever one's the largest number, then ultimately that's what your final answer would be, is who can win the most games. There's another way to do this. If we were to say 1, 2, 3 for each cow playing 1, 2, or 3, and then 1, 2, 3 for each cow playing 1, 2, or 3. Let me write down these numbers again. I have 1 to 2, 2 to 2, 1 to 3, 1 to 1, 3 to 2. Another way you could do this is you could make a 3x3 grid that represents cow A. What did cow A play? Actually, A should probably be on the row. And then cow B would be on the column. And then to start off with, you just count. So 1, 2 is row 1, column 2. So we'll put a 1 here. 2, 2, that's a tie score, but we'll go ahead and put a 1 there anyway. 1, 3, that's row 1, column 3. We'll put a 1 there. 1, 1, that would be a tie score, but we'll count it. 3, 2, row 3, column 2. That's a 1 there. If you do it like this, then you've got a 3x3 grid that shows just how much of each kind of game was played. There's one game where cow A played 1 and cow B played 1. There's one game where cow A played 1 and B played 2. There's one game when cow A played 1 and B played 3. There's a cow where A played 2 and B played 2, and a cow where A played 3 and B played 3. From here, then you just need to figure out what's larger between the numbers 1, 2, which would be cow A playing 1 and B playing 2, plus 2, 3, which anything I didn't fill out should be assumed to be a 0. This would be a 2D integer array, plus this number. So 1 against 2, 2 against 3, and 3 against 1. 1 plus 0 would be 1. And then compare it going the other way, where we have cow A playing 1 and cow B playing 3 being the winner, and then cow A playing 2 and B playing 1, and then cow A playing 3 and B playing 2. This would be the sort of the opposite then, because then I'd have 2 games won. I'd have 1 plus 0 plus 1, which would be 2, and that would be 2 wins, which is what we calculated before when we did the A++ and the B++. The difference between this method is in the first method, you're doing your if statement on every single number you add. Every single time you look at this, you're checking to see if A is greater than B or B is greater than A, and you're assigning a point. That's a lot of if statements, so it's a little bit less effective. It should still work within your time complexity. However, the reason I'm pointing out the second method is because just to start getting you thinking in terms of trying to do things in an efficient way. If I do an if statement on every single one of these, I have to do the if statement 100 times. On the other hand, if I were to just take these numbers as row column references and increment, I don't have to do an if statement to do that. I'm just increment, 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 which is very quick. Then once I'm done, essentially what I'm looking at is I'm looking at whether or not I'll have like A total. You could have A total be calculated as this array square bracket 0, square bracket 1, plus A square bracket 1, square bracket 2, plus A square bracket 2, square bracket 3. And then B would be A square bracket 2, square bracket 1, and then plus A square bracket 1, square bracket 0, plus A square bracket 0, square bracket 3. And then only after this, then you would check to see if A is greater than B, then A is the answer. Otherwise, if B is greater than A, then B is the answer. So just to kind of recap the 2 different methods and what the advantage to this one is. The advantage to this one is when you're running through looking at these numbers, we don't have to calculate or analyze. We just add to where they are in this matrix. And then once we're done, we calculate how many times in the world where 1 beats 2. So if 1 beats 2, that's a win for A. If 2 beats 3, and then if 3 beats 1, then that would be if 1 beats 2, 2 beats 3, 3 beats 1, which is we called like the world A. On the other hand, if 1 was to lose to 2, that would mean that 1 beats 3 instead. If 1 beats 3, then the implication is that 1 beats 3, 3 would beat 2, and then 2 would beat 1. And then that becomes the other direction, which is world B. If you do it this way, then you only have one if statement at the end, which is comparing A versus B. On the other hand, if you have the A less than B less than, or 1 less than 2 less than 3 less than 1 as your A world, and 1 greater than 2 greater than 3 greater than 1 as your B world, then every single one of these pairs, you have to feed through the if statement to decide whether or not you're going to do the +1 over here or the +1 over here. Or add to A versus add to B, which again isn't the end of the world. It still should run in plenty of time, within plenty of time, because I think they said the N was 100 games, and that's a tiny number of games. So when you see something like that, it's pretty safe most of the time to brute force such a thing. And I think actually with 100 games, you could pretty much pre-assign every possible combination of rock, paper, and scissors to the 1, 2, and 3, and run through and calculate all 6 possible. Would it be 6? Yeah, because you'd have 3 choices for the first one and 2 for the second one. You could really just brute force this all the way out if you really wanted to. But the simpler way to do it, the most straightforward way to do it, is either going to be choosing that as you go down, we're going to say, okay, if we've decided that 1 is going to beat 2 and 2 is going to beat 3 and 3 is going to beat 1, then does this a point for A or is it a point for B? Calculate up A's score and B's score and then invert them, or make a grid, keep track of how many of each kind of game was played, and then at the end, basically add up the diagonals and see which diagonal has the largest value. So that's Hoof, paper, scissors. Good luck coding it. I'll talk to you on the next one.